Hey, can you guys hear me?
I can hear you.
Great. My name is Danny. I'm the current captain for Virginia Tech's rocketry team. I think most of us are here, so.
All right. Let's get into it then. I have a few standard questions I like to ask just to see what everybody here says. So obviously we're not in the New Mexico desert launching a rocket, but let's imagine for a second that we are, that you've transported your rocket to New Mexico, that you are outside, it's 105 degrees Fahrenheit, and you're following the procedures you developed to put the rocket together. What problems do you encounter, and how do you plan on tackling them as you prepare for launch?
Yeah, that's a really great question. I'll take a stab at it, and then I'd like to pass it across some of our leads. Funnily enough, there's only one person in our current leadership that has actually been to IREX, so I'm sure he'll have some great insight here. But speaking from experience, we did a test flight, and there was some integration issues that kind of stacked up. And that was one of the biggest things that caught us off guard, is just how quickly like your timeline can sort of shift. Like we're targeting a 12 o'clock flight, and suddenly it's a 2 o'clock flight to like a 3:30 flight. And so keeping on top of your timeline is super important. One of the things that really helped us mitigate it in that test flight was working through our checklist really religiously, designating somebody that was only responsible for checking through boxes, making sure that everything was being done correctly, getting their own eyes on it, independently verifying it. And then another thing that worked out well for us is when we came across an item on the checklist that maybe it wasn't a mission critical issue, but like the item couldn't be completed as anticipated. We sort of went into a little leadership huddle with the relevant parties, talked through what our mitigation approach would be for that item, and then brought that up with like our RSO, the person signing off on our flight, our L3 flyer, and worked through the mitigation plan with them, and then had everyone sign that that was the plan that we were going to take rather than whatever we had originally anticipated in the checklist. Doing that in 105-degree heat, I don't know how that would change things. I'm sure tensions get high and everyone needs a second to work through their emotions. But I want to pop this off to Salim if you have anything to add here.
Yeah, I mean, what you said is spot on. And just to add on to that is when it's 105-degree heat, I mean, last time I was there was 4 years ago, but it pretty much everything, all your emotions get pretty high. You're very excited to launch. You're like, oh, this is it, very excited. And you start doing things quickly. And sometimes you might, accidentally do something too fast. And, that's where the checklist comes in, as Danny was saying, that it's really important for us to have someone who's kind of watching over our shoulder and be like, hey, this checklist says that you need to do X, Y, Z, but like you did it super fast. Are you sure that you did all this in order and correctly? So it helps to have someone to kind of be there and be like, just take a deep breath, slow down, check everything in, and then take a look at what you just did and make sure that what you did is correct, so that when it comes time to fly, hopefully there's nothing wrong with it and everything works out well.
As an extension to that question, my next phase would be, all right, so you got the rocket on the rail and it goes and launches. What do you think are the most likely failure modes, and what is the consequence of that occurring during the flight?
So yeah, I'll throw in my thoughts here, and then again, any other leads if you guys want to speak up. I think from our previous flight, one of the most mission critical failure modes that we unfortunately had was a failure for chutes to deploy. I wouldn't say necessarily that's the most likely. There were some specific issues that in post-flight analysis we figured out would need to be addressed for moving forward. But yeah, that I would say is one of our biggest concerns that we're tracking after we do fly. After that, we have some systems on board that I think you have to be very careful with how you, when you're working through your integration checklist to make sure that those systems are primed correctly and that they're failing safely if they do fail. So I guess, does anyone else have any thoughts here? That's okay.
All right. And then considering this, obviously we're not flying in the desert this year, but you guys have done a lot of work preparing a vehicle. How are you planning on capturing the lessons you learned this year and your experience and transferring it to yourselves or another team for next year's competition?
We're actually lucky enough to have some people that are going to be taking over for next year. So I'll toss this over to Hannah or Zach if either of you want to try and raise an answer to this.
Yeah, one thing that we are going to do is we believe that a large part of the problem is the electronics bay. And so we plan to work more closely with faculty and the local AAA chapter on that. We're going to have more frequent faculty meetings. We are going to have a smaller, simpler rocket, and we plan to do more tests. For one thing, we plan to test the recovery system on a smaller rocket to make sure that the electronics work correctly for a lower altitude flight. That's what's come out of discussions with faculty so far. And Hannah, if you have any thoughts to expand on that, then.
So Rocketry at Virginia Tech has been a team for a while now, and very quickly in rocketry's history, we had the goal of competing in Spaceport America. So throughout our history as a design team, there have been a lot of cool different ideas, projects that have been attempted by different sub-teams. And I think that next year, one of our main considerations as we're working through our design process for the year is to make sure that we are all properly working together as one team and returning possibly to fundamentals to make sure that we return to that initial purpose when rocketry first became a team. We're much bigger now than we used to be. Initially, the team was closer to like a group of like 8 people who just wanted to launch at Spaceport America, whereas now, leaving this year, we had about 50 people on the team. So you have a lot more members to manage. You have a lot more complex projects that you're trying to integrate into one rocket. And so we really want to emphasize safety and fundamentals and really good working together between the sub-teams to make sure that we can all reach our final goal of Spaceport in as seamless a fashion as possible and producing a really good rocket.
I think
to kind of touch on that.
Oh, yeah, go ahead, this one. No, you're good.
Okay.
You got it.
To kind of touch on that real quick, I know one of the sub questions you had in there was how we're trying to pass on the information. We use Microsoft Teams as our kind of internal communication system, and we have something in there called wikis, and they're pretty much just like, imagine like a Wikipedia, but we have them for each sub team, and we fill in information about, you know, what we've done, the kind of tests that we've done, processes that we've gone through, and it's a way of our internal documentation to make sure that, you know, that information stays there for years to come, to make sure that, you know, if they want to take a look at how we did something, they can just go back to that. And then on top of that, there's also the report that we submit to you guys. And I know that's not like that's not the only way of documenting anything, but it's also really helpful because it provides us a good summary of what went on. And then they want further information, they can come back to the wikis and kind of delve back in deeper for that.
That's pretty much what I was going to say. I was just going to add on that, like, some of the leads are creating specific like documents for their like teams. That way they know what happened this year, what should have happened, why the design choices that were made in prior years were made, just based on things that they've learned and stuff like that. Because I think a lot of the issues that come up is a bunch of like technical debt that just sort of builds up over time, where people make certain choices that they make and nobody knows why those choices were made. But like there was a reason for those choices. And I think another thing that we really tried to do this semester that I don't think we've touched on yet is talk to prior years, because we had like actual discussions with alumni from this team that were able to help a bunch of these other specific sub teams doing whatever they were doing. We've got one of our graduate students who was the software team lead, and he's back on the team now, and he's helping us sort of work through some of the problems that we're running through. So just being able to talk to prior years in the past has also definitely helped us just sort of learn how to carry on that knowledge better, I guess.
Did you call that technical debt?
I don't know. That's just the term that I've used. I don't know.
It's a good word for it. Just wait until you get into the industry and find how much debt there is.
Oh, do.
Mark or John, do you have any questions?
This is Mark. Something I noticed in the presentation, you had recommended redundancy in the ejection system. And that was part of the DT&E guide for redundancy. So I wonder if that's something that you overlooked, or you just assumed that it would be okay.
So I think Salim should really clarify this. We did include redundancy, though. I will start by saying that. So Salim, if you want to go in more depth there.
Yeah, sorry. I guess I misunderstood your question a little bit. Are you talking about the redundancy for the ejection or recovery? I didn't quite catch that. I'm sorry.
Well, recovery and ejection, is there a difference there?
Okay, to me, in my mind, my recovery is the GPS electronics, and then the ejection is the like stratologgers that keep track of parachute stuff. That's just the way I keep it in mind. So I always like to clarify which one I'm talking about first.
So how did you interpret the DT&E guide as far as redundancy?
Just to make sure that there are, isolated redundant systems that we have in the rocket to make sure that, if one fails, that it doesn't kick everything down and mess up the entire rest of the rocket. So we had 3 independent stratologgers, each with their own battery systems for the ejection, to make sure that, parachute ejection was redundant in that case too. So we had triplex redundancy there. And then for our recovery systems, which for me is the GPS, we also had 3 independently powered GPS systems to keep track of where the rocket was and where it landed. Does that answer your question?
Well, what was the redundancy that you recommended in your presentation?
Unfortunately, I was unable to be there for the presentation. I had a prior conflict, so that was another member of my team. So if you have like a specific word or phrase that they were using that I could elaborate on, I could try to do that. But
I think I can touch on this, Salim.
go ahead.
So the way we kind of structured the presentation is to sort of take a look back at how things went this year and what we were planning on changing based on that moving forward. I think the key word that we were missing in that presentation, and if we could go back and redo it, we should have really drove this home, is dissimilar redundancy. One of the issues that we ran into is we did have, different stratologgers on their entirely different power systems, all trying to accomplish the same thing, but they all use the same battery holders. And that's one of the things that we think ended up failing in flight. We think that there was maybe a loss of connection with the 9-volt to the actual stratologger. So that's the word there. It wasn't in the presentation, that's our fault. But dissimilarity is the biggest thing that we want to look forward to. How can we accomplish dissimilar redundancy is a big problem or thing that we were looking to address moving forward.
Okay.
I guess one thing I'd be interested in is if somebody could speak a little bit to the design of the air brake system. I thought the CFD analysis for determining the drag was fairly interesting and a good level of detail to go into. I'm curious about how to integrate it with the rocket. I noticed you have it modeled at the back at the fins, which makes a lot of sense, but where is that process at the moment? How do you plan on implementing it into the awesome structure that you have built?
Jacob, do you want to talk about that, or do you want me to take it?
I think you can take it as far as like physical integration.
Okay. So Jacob's the head of our design validation team. He's the one that's doing all the CFD simulations, and the way that we're planning on integrating it is to kind of have almost like a lookup table in our code that would be previously validated solutions from the CFD analysis that tells you, if we're flying at this speed and we're at this altitude based off of the sensor data that we have incorporated into our system, how much drag we can expect with various extensions of our active drag system. And by doing that, we can incorporate that into our model and determine where, what our expected apogee would be and which, actuation percentage would be the best to get us there. Unfortunately, there were some parts that broke when we were testing our active drag system, and they weren't able to come in for our test flight, so we weren't able to incorporate it this year. But next year, we're planning on having, hopefully more tests and actual flight data to back up this information and see how well it incorporates into our rocket.
You might have mentioned it, but I want to just ask to make sure it's in my head. Is it a continual adjustment, or does it just make a couple steps at different points in the?
Gotcha. So the idea is continual adjustment. In our previous years, we had an Arduino controlling it, and one of the major downsides of that was there wasn't enough processing power to kind of run this model, so it'd run at 2 hertz. So the continuous adjustment was there, but it's almost like it was only doing it once or twice throughout a burnout phase, just because it was so slow. So we've moved on to our stronger platform, the BeagleBone, which is kind of like a Raspberry Pi. And the idea for that is it's more powerful, so we should be able to get better frequency in terms of our continuous adjustment.
Mm-hmm. And then I saw the CAD diagrams of how the actual actuation arms work. Whenever is it, and I want to try to understand where it physically is in the rocket. Is it situated forward of the motor tube, or is there some linkage that brings it backwards? How is it ultimately going to be constructed, I guess?
Right, so we constructed it, and it would sit immediately above the motor tube and beneath our electronics bay. We want it as low as possible to make sure our CP doesn't, do crazy things and, shoot up throughout the rocket. So it's there, and then the actuation linkages are actuated with a servo that sits within the housing itself. So it's completely self-contained, and if we wanted to, we could move it somewhere else in the rocket. We just chose that because that's the aftmost point that we could put it.
Yeah, makes sense. I guess a further question about the structure. Was there a defined requirement or need for the carbon fiber Nomex sandwich? Or is that just something cool because it is? But I'm wondering how that evolved and what decisions were made there.
I think I'll throw my thoughts here and then I'd like Hannah's thoughts on this too. So I think it kind of started a few years ago as like this cool factor. I remember there was an older lead that spent like a month or 2 months, like a good portion of time just trying to get the layups correct. And they perfected that layup process. And then, last year we couldn't fly because of, the shutdown and everything. So we recycled some of those old parts. So this year kind of became a requirement because it simplified our manufacturing process. But in previous years, it was just because it's so cool. Hannah, do you have any thoughts here on sort of the benefits of going with that approach?
I know that when they were first considering like how to manufacture their body tubes, because initially I was talking to previously the guy who initially created this process about like, why wouldn't you just take like cardboard body tube and then wrap it with carbon fiber to reinforce it? And he said a lot of what they were considering is that they were really trying to optimize as minimum mass as possible, because they had a lot of other subsystems that were heavier in mass. So they didn't want to have to add any extra unnecessary weight from the structure while also not having to compromise the strength of the materials at all. And so through a lot of research, they ended up developing a similar process for both our fins and our body tubes. And I'd have to find the exact number, I guess, if you're interested, but they ended up compression testing the body tubes to end up holding a very large amount of weight. And I can look it up real quick if you'd like me to.
Well, it's good that you've done the test, but I don't need to know the figures right now. Mark or John, do you have any other things we should ask them?
Yeah, I had one question. I know here you had on the motor you selected was an Aerotech N3300. Have y'all utilized that motor before?
No, this would be the first time we used that motor. Our test flight was on N2200, and that put us to about 7,000 or 8,000 feet in sims and what we think our real flight apogee was. One of the advantages of the N33 was that we're trying to develop a hybrid propulsion system, and we had worked out a way where we could keep the rocket so that it can accommodate the hybrid propulsion system and use the N33 in sort of a heavier structure vehicle architecture to get to 10,000 feet if we needed a backup plan, more or less.
Okay, that's all I got. Thank you.
Al, this is Cliff Olmsted just checking in. What team is this?
It's Virginia Tech.
Virginia Tech. Okay, thank you.
And I think we're just about ready to wrap it up. Just a final thing, is there anything that you guys would like us to know about your project that we possibly haven't covered that we should know about?
I think the only thing we didn't really touch upon is that we are working towards doing an injectable payload. So that's one of the systems that we're trying to add complexity, but also trying to keep our fundamentals strong. So that's just something that's in the works that might be good to know. Neha, I don't know, do you have any thoughts here really quickly?
Yeah, I can talk a little more about that if you'd like to know about what our goals are there.
Yeah, sure. I think we're kind of running out of time, but go for it.
Yeah, if you can just take another 30 seconds or so, that'd be great. And then we do need to end here because we've got other teams waiting.
Sure, I'll give you a 30-second summary of what we're trying to do. So our goal for our payload is to eject out of the rocket at apogee, and then we want to implement an autonomous flight guidance system that steers it down to where we want it to land on the ground. So this year we worked on vehicle eject, and then in the future we'll be working on that flight guidance system.
Yeah.
Yep, and that's it.
So we're looking on a lot of different things here. Anyway, thank you guys so much for your time. If you have any questions, feel free to reach out to us.
Thank you so much.
Thank you guys.
Thank you.
Have a
Thank you
good
very
day.
much.
Thank you.
Hi, Curtis. Hi, Mark. Good to see you.
Hi, good to see you too. Or